So we're going to first start by talking about topic modeling and what topic modeling is and why you might want to do topic modeling. So let's all picture for a second that we're all working for a newspaper agency. And our unfortunate job is now to organize all of both the internal documents and the documents which are part of the newspaper articles. So you have sports articles, you have weather articles, you have articles on politics, and none of this is labeled. So our idea or motivation, for example, here is to try to get some structure out of completely unlabeled textual data, any form of textual data. So now one approach to actually go about doing this is to try and see if we can find out what topics are inside a data set. So for example, if you're looking at newspapers, if you are writing a newspaper article, let's broadly say we have 3 topics: politics, sports, and the weather. Dreadfully boring, but this is our job now and we have to do it. So one way would be to say, okay, I have all these news articles and I'm going to guess there are around 3 topics and I'm going to fire up my topic modeling algorithm. And what I'm going to get are a bunch of words which represent a topic. For example, if I run this on maybe 2017 newspaper articles, I'd get an article, unfortunately, about American politics and Trump and so on and so forth. I'd get one thing about weather. And if you live like me in Lille, it's going to be depressing weather, cold and rainy all the time. But basically, depending on the kind of articles you're dealing with, we'll be getting different kinds of topics, and depending on the numbers. So you can try and figure out why this might be a nice way to sort of just put all of your documents into different topics. It's also interesting to try and see what kind of words and what kind of ideas are in your data set. So there's a lot of motivation for using topic models. And what we're going to see throughout the tutorial, what exactly topic models are and why it might be useful. So now that we all have an extremely rough idea of what topic models are, that's completely enough to actually just dive in. Now, the second part about the tutorial is I probably should not have actually named it a topic modeling tutorial, because there's not too much of topic modeling. There's actually more of text pre-processing. Now, why there's more of text pre-processing is when I was first doing this tutorial, and it was only a topic modeling tutorial, I realized I was getting really, really rubbish results when I wasn't pre-processing my text. And I figured, hey, this is actually more important than my actual topic models. My actual topic models are one line of code, which Gensim helps me do. So what we're going to do in this tutorial is actually figure out how to clean a data set and how to set it up to get it ready for topic modeling. But not just for topic modeling, for any kind of textual analysis. So our focus here is more about good practices in text analysis in general, which is going to be super helpful for our actual topic modeling. You can also, of course, do all sorts of text analysis with this, Word2Vec, and so on and so forth, which Gensim also has. Now, what I would want everyone to do if everyone has their models downloaded in an ideal world would be to start the Jupyter Notebook. Can everyone see? Yep, so, well, yeah, this is the Jupyter Notebook, which I'm going to be using, which everyone should be using. Now, there are 2 things you folks can do. You can either go to my repository and find the already run Jupyter Notebook, which has every single cell of this notebook already run. So you can just follow that notebook and look at that. Or you can watch me while I press enter on every single cell, which is also fun, I guess. So really, the only thing you are missing out by not having the language models is not pressing enter on the Jupyter Notebook. But it would be the reason I spend so much time on actually insisting on setting up the environment is so you can go home and do what I'm doing right now. Because the real fun of text modeling is trying it on your own textual data. So it's not a huge deal if you do not have the environment set up. But it would be worth your while to go home and actually set it up so you can run this notebook later. So let's start. So, well, for those of you who do have everything set up, your first step would be to get your imports done. And let's talk about what data set we'll be using for this particular task. It's a terribly boring data set. It's the news data set. Well, in particular, it's the Lee background corpus. You can actually see, you can click on the link and go and check out the research paper which started using the corpus. As far as we're concerned, we're going to use this data set because it's small and because it's available in Gensim. Gensim has this as one of its default data sets, and it's super easy to get running. Again, for those who have the Jupyter Notebooks run but are using Python 3, please comment out this piece of code. Yeah, for me, because I'm using Python 2.7 because I figured it's some people might still need to, so I might need to have these functions. This should work normally. So what we're doing over here is we're loading our data set. So text, as you can see over here. OK, let's actually see what text looks like. Yep, so you can see that text is, yeah. You can see that it's new line separated for each different article. You can see that more clearly after we run the spaCy language pipeline. But so far, our idea, I mean, until here is just to load our textual data set. So this is the data set which we'll be playing with. And now, and this is super important because it's actually the bulk of our problem. I mean, we're going to be solving every single pre-processing problem with just a small line of code, which is over here. This is what I wanted everyone to download, which is the spaCy English language model. Now, I would like to also talk about NLTK because it's also a popular choice for text pre-processing. In fact, most of the text processing tutorials I've seen do their stemming or lemmatizing or whatever cleaning using NLTK. I would really recommend not using NLTK. You can see in this article, which is linked over here in the notebook, that he talks about Matt Honorable, who is the creator of spaCy, talks about how terrible NLTK is because of how much it's research-oriented and not really fit for industry or production-level code. So I would really recommend reading this article and really feel motivated to stop using NLTK. The article is actually, it's pretty mean. It sort of says why dead code should be buried. Yeah, so he really does not like NLTK. I'm not a big fan either. I would really recommend using spaCy, and a huge part of this tutorial is actually motivating people to check spaCy out and to show why it's super awesome for text processing. So this one line, by the way, if I'm going too fast or if you have any questions, please put your hand up and I'll stop. But yeah, so in any machine learning problem, if you're going to give rubbish input, you're going to get rubbish output. So let's really focus on cleaning our data set here. Over here, what we're doing when we do NLP is equal to spaCy.load.en is we're creating a language pipeline. So NLP is now our English language pipeline. Now, what I'm going to do right now is I'm going to start walking you through the process of text pre-processing. So in this particular case, let's talk about stop words. Stop words are words which we think add no information to our textual analysis. So in my experience, and this I actually figured out after doing my topic modeling, I ran a couple of topic models on the textual data set, the news data set which you folks saw before, and I kept seeing words like say, Mr., and well, different kinds of words which are built on the word say. And I figured that, hey, say is not adding any actual information to my stop words. So what I decided to do was add the word say to my stop word list. Now, how do you decide whether a word is a stop word? spaCy, when you download the English language model, has built in a lot of words which spaCy thinks are stop words. There's also a German language model. So if you are working on German language data and you download the spaCy German language model, you'll have spaCy German stop words. And if you want to add more words to the stop word list, you do it like this. Now, how did I figure out that you have to do it like this? Stack Overflow, I had no clue. So basically what we're doing here is my stop words is my list of stop words I want to add to spaCy's list of stop words. I'm going to loop over these, and for every, here lexeme is basically I'm applying my spaCy pipeline on the word, the stop word, and I'm making sure that it's a stop word by saying is stop is equal to true. So it's that simple. If I want to add any more words, I just add more words to that list, and I have more stop words. Now, about the motivation of stop words, again, it's because I knew that these words were words I needed to add because I knew how terrible my topic models were once I saw them. So really, adding stop words and knowing which words are your stop words is really a trial and error game where you sort of look at your topic models or look at words that you think are relevant to that data set which are not going to be relevant to the topic models and figure out which words to add. So are there any problems until here? Yeah? Cool. So now in this particular cell, we are doing, it's going to take a small while. And for those who are using Python 3, you're going to have to remove the clean part, because if you remember in cell number 2, we commented that out. So we would need to do document is equal to NLP of text. So once it's done, we're pretty much done with our pre-processing the moment we've done this, which is why I really like spaCy, because you don't need to do step by step. The moment you put your text through the pipeline, through spaCy's pipeline, we now have a lot of interesting information. I'm going to show you what kind of information we have. Has anyone run this particular cell? Yeah? Cool, awesome. A couple of people are there, okay. So now we're going to see what this looks like. Now I reckon this is the most important cell in the whole notebook. So let's sort of look at our output. You can see hundreds of people have been forced to vacate their homes, so on and so forth. That's the beginning of the text. So what's happened over here is each word in the document. So it's sort of looping through every single word in the document, and it's assigning certain properties to these words. So for example, you'd find out if a particular word in this document, is it a stop word? Is it a number? Is it a verb? Is it a noun? Is it a name, place, animal, or thing? You find out different properties of each single word by running doc. So by passing your text through spaCy's language model, you're assigning properties to every single word. Let's see how this works. I'm going to really emphasize on the magic of spaCy over here, which you can see in this cell where we're constructing our corpus. Now, a corpus here, at least from Gensim's point of view, you can actually see the link, which sort of takes you through the page where you can see what a corpus looks like. But from our point of view, a corpus is a list of lists, where each individual list inside the list is your document. And it's actually easier if I show you, I think. So if I look at texts, you can see it's a list of lists where every single word is separated and broken up. So for example, we saw hundreds of people have been forced to vacate their homes, blah, blah, blah. What we've done after that, I'm going to walk you through every single line in cell number 8 to show you exactly what's going on. So we have to start here. So we have two lists, texts and articles. So again, a Gensim corpus is a list of lists, where every single list inside is your document, cleaned up and separated. So what we're doing out here is for every single word in my document, if the word is not a new line, which means if it's not the new document, if it's not a stop word, remember we don't want stop words in our documents because stop words add no interesting information. If it's not a punctuation mark, and if it's not a number, I add the lemmatized form of this word to my article. Now, what does lemmatized form mean? It's basically the root of the word. For example, saying, said, would have say as its root word. So we don't really care about the kind of word, we only care about the context, so we only add the lemmatized form of the word. So here, using spaCy, I'm figuring out if it's a punctuation mark, if it's a stop word, if it's a number, and if it's not any of these, I'm adding just the root to my document. Can you see how easy spaCy makes our job? We can also, for example, say we want to add only verbs. You could actually make sure, you could check what kind of part of speech that particular word is, and you can have a topic model with only verbs, or only nouns, or only numbers. So what I would like to emphasize on over here is that make sure you understand every single line, because depending on the kind of data set you're dealing with, you're going to have to be pre-processing your text in a different way. You might want different things in your final text model, topic model, and you might not. So what we're doing over here is extremely simple. We're just checking if it's not a number, if it's not a stop word, and I'm making sure to add the lemmatized form to my final corpus. Let's take some time here to try and figure out what's going on. Are there any questions, or is anyone slightly confused? Yeah?
You said it also knows which ones are verbs?
Yes.
What else does it know?
It know the part of speech, noun or verb, and so on and so forth. You could also find out if it's, it does NER, which is named entity recognition. For example, your language model is trained to know if it's a place, a location, a geopolitical, a work of art. So for example, if I would actually talk about this here. Okay. Okay, it's actually in the end of my this thing. I basically talk about what all spaCy has to offer, apart from text pre-processing. So in our particular case, spaCy is really useful for the job because once we do doc is equal to NLP of text, we're basically all our text is being processed by spaCy's pipeline. The only information which we are using from this is whether if it's a stop word or if it's a number, pretty basic things. But you can get really funky with this and use all the properties of spaCy's lexeme to try and figure out what kind of data set you want to build. So while we won't be talking, and also we have lots of different languages. There's also the French, German, English, and I think they have things like Hungarian in alpha mode and alpha. So you can, like, whatever, there's a lot of language support over there. You can actually check, I would really recommend checking spaCy out and seeing all the cool things it can offer. In our case, we're only going to use it to clean our data set, which is, again, in this particular cell. You can see exactly what's going on, if it's not a new line, and so on and so forth. But you can really go crazy with this. I'm going to leave this, since this has nothing to do with topic modeling, I won't go into it. But this just shows some of the power which spaCy has. Does that answer your question? Yes. Oh, and by the way, the question, yeah. Yeah. Yeah, it's super cool. So it's trained using a neural network, and before they use more traditional linguistic rules to figure this out. Now it's all done on neural networks. Of course, accuracy, it's not going to be perfect every single time, but you can keep training it and making it better. And like, since this huge motivating thing is the fact that they have language models in many languages. French, German, and I think Spanish is being worked on. I think someone's doing Norwegian. So you can, yeah, check spaCy out. It's totally cool. And as for creating our corpus, this is what we're doing. You can I would recommend seeing texts. Let's look at just our first document. So you can see how it's been cleaned up. From hundreds of people have been forced to vacate their homes. We have hundreds of people forced to vacate home. You can see what we're doing out here is only keeping key information from the original text. And this is extremely important in text processing, because I don't need words like off and they're not going to add any information to my topic model. So by using spaCy and not NLTK, we have super fast text modeling, and you can also use spaCy for other things. I've linked to different notebooks and different projects you can use only using spaCy at the end of this Jupyter notebook. So totally check spaCy out, which is why I was insisting on getting the language model downloaded over here. But even if it's not, you know what kind of problems to experience while downloading the language model, you can go home and do it. I would really recommend that. Are there any questions about why a Gensim corpus looks the way it does, or what, if you've understood what a Gensim corpus is supposed to look like, and also what spaCy is doing? Yeah?
Yeah, I had a curiosity because you're using lemmatizing. So why did you add say, said, saying, and so on to the stop words because it just had one?
Yeah. So it's a good question. The question is, why did I add all say, all the different kinds of words which stem from say and not just say? This is because the stop words does not look at the lemmatized form. The stop words look at the original word. So what I could have done w.lemma is stop as well. But I just decided to add all the different kinds to give more of an example of how stop words are. But I hope your question is answered. I could have done that too. Yeah. Is there anything else? We can really spend lots of time over here, because after this, it becomes rather trivial. We're just going to be using Gensim's topic models to find our topic models. This is really the most important part of it. Like, cell number 8 is what you'll really need to understand and appreciate, because in a few lines of code, we're really creating a corpus, which is really cool. And the best part is you can use this for Gensim, for scikit-learn, for whatever kind of text processing, machine learning algorithm you have in mind. Yeah?
Does it recognize sentence structure already if I do the NLP?
Oh, yes, it does. So you can. You can do that. Yeah. Again, so since this is not relevant to generating our topic models, I'm not going to get into it. But there's actually, like, for example, they've done something called, I think, LDA to sent. So they actually use sentiment analysis and LDA, and they analyze Reddit. And they have a lot of cool projects on the spaCy page. spaCy are not paying me, by the way. I just really like spaCy. But yeah, you can do that. You can find out sentence structure, trees, and a lot of cool things. So again, just to emphasize, by running spaCy's language model on our text file, we're also learning about things like nouns and parts of speech, but we're not using them. The only part which we're using is stop words and numbers. So it's still extremely useful, and also lemmatizing. So it's still extremely useful for us, but we're only really touching the surface here with spaCy's power. So is this part clear? Have you understood what a Gensim corpus is and why it looks like that? Yeah? Cool? Awesome. Yep, so like I've just been saying the whole time, we're only using this much. Now we're going to use our first Gensim, the first bit of Gensim, which is actually something called bigrams. So again, bigrams are something which I figured I should be using after I got really rubbish results in my first topic model. The same way I figured out which stop words to use. So what bigrams is, we're going to be, for example, when some words tend to appear around each other more commonly, like New York, makes more sense as New York rather than New and York. So we decide to combine them. I've sort of given the motivating example over here. And if any of you are following my Jupyter notebook, which is already run, you can actually go down to the first topic model and you can find words like bin Laden instead of bin and Laden as two separate words. So you can understand the motivation of why you would need to use a bigram. It's because sometimes the word bin Laden makes more sense to me than bin and Laden, or New York makes more sense to me than. Another important thing out here is our model, our textual data set which we're using is actually the Australian broadcasting data set. So New York is not a word which is going to come up. So if the word New York existed in one particular sentence in this data set, it would actually not be found. Because what bigrams do is for that particular data set. So you'll find things like New South Wales and bin Laden because these were bigrams which are brought up quite often in that data set, but not other ones. So you can actually see what goes on by over here. Though I'm not sure if you can see it immediately, but oh yeah, can you see New South over here? And if you look at text over here, it was New and South, two different words. So we're creating bigrams super easy, and it's yeah. Why did I use bigrams? Is because again, like I said, I looked at my topic model and I found out I was getting more information when I used bigrams. You could so it's really something which you sort of figure out you might or might not need, but I think it's an important concept to know when you're working with NLP in general. Is that clear? Yeah? Over here? Oh, actually, so over here in phrases, I'm actually not 100% sure. Lev, do you happen to know if does it default, does it pick up bigrams, or does it? Yeah, is that okay? So the question was whether, I'm sorry, I'm supposed to be repeating questions. Whoops. The question was about whether I had to specify it was bigrams or trigrams. No, the default is bigrams like Lev sorted out for you. So is that part clear? Can we move on? Yeah? Yeah? I'm sorry? Could you be? No, it's just the most probable bigrams. So for example, I don't know what else. For example, 100 people has not come across so many times, so it wouldn't pick up 100 people. But it's seeing New South Wales a bunch of times, so it's, yeah. Like for example, if I was running it on the Harry Potter books, then I might find Harry Potter, but not Ron Weasley, because no one really says Ron Weasley. They just say Ron. So, okay, cell number 13 is also quite important because what we're going to be doing is we're going to be converting our well, we're going to be converting what our data set looked like over here, which is texts. We're going to be converting that into a bag of words format. Does anyone here? So bag of words is a representation where we count the number of occurrences of each word in that particular document. So I'm going to show you what exactly it looks like. So basically what this means is that, again, it's just a list of lists, but here document number 1 says that word ID number 0 occurs one time in this particular document. So what we're doing is we're basically mapping every single word to an ID, and then we're making a bag of words out of it. Is that clear, or do I need to explain this? Yeah, all cool? Okay, so we're pretty much done with what I think is an important part of this, which is creating a clean data set which we can actually work on. This is sort of the key takeaway, and right now we're going to sort of be talking about what topic models are and how we're going to use this corpus which we created. Yeah? So the question, I'm sorry, I'm just going to repeat the question. The question was about if you what's going to happen if you run trigrams and so on and so forth. And the answer is if you run the bigram again, it's going to create trigrams and so on and so forth. Yeah? Can we use what do you, the question is can we use it for semantic modeling, but I'm not sure what it is. What did we create apart from the corpus? We just created an easy way for us to do our text analysis. We created a corpus.
Yeah, but can we use that corpus? So we are doing topic modeling now, but can we use that corpus for semantic modeling too?
Well, it depends on what kind of input your semantic modeling algorithm accepts, but if it accepts a bag of words format, then definitely, yeah. So the main idea here, again, was sort of to introduce everyone to what spaCy can do and how to include spaCy in your natural language processing pipeline. So now that we're done about spaCy, let's actually move to topic modeling. Now, I briefly talked about what topic modeling was and why we might need to use topic modeling before we started off. So let's see what's going on. And one of my favorite parts about topic modeling in general, or in this particular case about Gensim, is how easy and how you don't need to worry about any mathematics or any of the, it's a black box and you can use it really easily. For example, out here, it's absurd what all, you just need to tell the number of topics and pass the dictionary and corpus. And if you don't have a corpus and dictionary, then you're not doing any text modeling. So literally the only thing which we needed to tell Gensim here is the number of topics. That's it. So the algorithm which we're going to be using is LSI, or latent semantic indexing.
One quick question about
Yeah.
bigram still. So why does it get, given that usually it's going to be New South Wales, why did it get New South and didn't also get South Wales?
So the question is about bigrams. Why did it not pick up South Wales and only picked up New South? So, well, my intuition is, and I'm not completely sure, but in the data set, I think that New and South could have been something else as well. Or, no? Okay, that's probably the right answer. Yes. Yep. I'm sorry, I've not actually worked on the phrases part of the module, so I'm really not sure Lev would be much better at answering these questions. Oh yeah? Yeah, so it'll be faster. Yeah. Okay, so yeah, so what we're doing over here now in line number 16 is we're running our first topic model on the corpus with 10 topics. Now we're going to look at the top 5 topics over here. And yeah, and all of you who are running a Jupyter notebook yourself might be getting slightly different topics. That's completely normal. So yeah, so we can see exactly what a topic model looks like. I previously talked about how each topic model is a collection of words. So you can see over here that topic 0 is about the Israeli-Palestinian conflict. And so is topic 2, but topic 4, which is ID number 3, is a little more interesting or less interesting, depending on, it's about firefighters. And yeah, so you can see we only use 10 topics over here, but this is what a topic model looks like. Yeah, that's also because the minus and plus, which is why I move on to HTTP and LDA, which is, I think, more. So over here, the numbers can be deceiving because if only the modulus counts. So this is just to give you an idea of what a topic model looks like. Basically, we can interpret each topic as a distribution of words, and we can think of each document as a distribution of topics. So this means that topic 0 has the following words, and each document would be made of a distribution of topics. So if document number 73 had 45% topic 0 and 20% topic 1, and maybe the remaining 25% in topic 3, you can understand what each document is made of. So a document is no longer just a bunch of words put together, it's a bunch of topics. This, yeah? So I actually get asked this question at every single time I do this tutorial, and so I always Google it, and actually it does not matter. I'm going to need Lev to again confirm on an LSI at least on. Yeah. So in this particular case, I would ask you to actually just ignore that. So, but in LDA and HTTP, yeah, I'm sorry? So this is just to give an example. Like normally I put LSI over first because I don't like to talk about what it is, and also because I just want to give an example of what a topic model is supposed to look like. When we move on to LDA and HTTP, which is right below this, so I can actually explain. You're going to figure it out, but yes? Well, that's actually because of the number of, that's actually the show topics method over there. I put it as 10 because if I do 20 or 30 or even longer, it's going to stop making as much sense. Because then all of them are going to look like the most probable words in each topic. I can, hold on. Well, to answer your question, basically, each word in your vocabulary has a number associated with it. We only look at the highest values, or the most relevant ones. You can see this a lot clearer in the HTTP model, where unlike the LSI, you can actually interpret the topics. For example, you can see here in topic 0 that it's 0.007 Israeli, which means that topic 0 has that percentage of chance of having Israeli being represented by that topic. I'm sorry? Oh, yeah. So here, this would make a lot more sense. You can actually see, well, yeah, so this means topic 0 has that topic distribution of words, and topic 1 has a distribution of words, and so on and so forth. And you can also see there are more words here. So you asked why I only had the top 10 words. It's because I chose the top 10 words as a default number of words I'd like to see. You can see the top 20, top 30, but they're not going to make as much sense because every topic is going to start looking like each other after that. Yeah? Yes? Oh yes, you would, because it's randomized. We're not going to be getting the exact. If we fix a random seed, then we'll get the exact same topic distribution. But because we're all running different random seeds, our topics are going to look slightly different. Yeah. Yeah. So wait, yeah. Of course. Definitely. So I would call it my Israeli topic, but it could also be topic. I would rather call the proper way to call it would be topic ID number 0, and topic ID 1, and topic ID 2, and so on and so forth. So well, there are a bunch of ways you can do it. One would to actually look at the topic, but I'm also going to be talking about a really handy kit called PyLDA, which sort of allows you to visualize these topic models, so you can interpret the topics in a cooler way. But the way I would do it is just actually go through it. So it's manual. We'd actually have to go through the topic and figure out what you'd want to call it. Because, for example, you can choose to interpret a combination of words. Different people can interpret a combination of words in a different way. So it's just what I would call the Israeli topic and the firefighter topic. And there's one about Hare Krishna and Ganges and stuff like that. I'm sure it's gone over there, but yeah. So each topic can be interpreted by the person in a different way. Yeah?
Each word in the vocabulary will actually belong to exactly only one topic, right?
No. So what happens is you would also notice that, for example, Australia is in a bunch of topics. Yeah? What it means is that topic 3 or topic ID number 3 has extremely high probability of having the word Australia in it, and other topics would not. So every single topic has every single word with different probabilities. So the reason I would not do top 100 words would be because it's highly likely the last 90 words have no relevance to the topic.
So then, for example, if document 1 is having is composed of 40% of topic A, then it means that the 40% weightage of these words is in the document.
You can think of it like that, yes. So is it clear what exactly a topic model is? Because this is a topic model. So please, we can take some time here to answer questions. So that's actually a good question. So each topic model performs slightly differently, and we'll also be briefly talking about how to compare between different topic models at the end of this notebook. But yes, each topic model is slightly different, and it might not be the topic model for you. So each topic model, again, depends really on the person and for the task at hand and why you want to use it. So we'll be talking about comparing models at the end of this. Yes?
Just as a side note, there's going to be a whole talk for
Yes. Yes, there's also going to be a talk tomorrow only about comparing topic models but in the afternoon, I think 3 p.m. or something. So please, that would be a really nice way to make sure you actually understood what's going on here. Yeah, anything else? Cool. So we're going to now, so the HTTP is the hierarchical direct process. This is super awesome. If you notice, we only put the corpus in the dictionary. We could not be lazier. We did not, it's almost requires no parameters, and it's really neat. Now let's look at LDA. So you're going to see that these topic models behave in pretty much the same way in sense of what the output is. It's just considering the fact we're treating them like black boxes at the moment, we don't really need to know what it's doing. But apart from the fact that we need to realize why the result looks like the way it does. So you can actually, if you're running this on your own machines, you can actually look at your LDA topic model, your HTTP topic model, and see how it's different and the quirks and play around with it. Any questions? You'd also be probably getting slightly different topic models compared to the ones I have. So now we had a question about how you can interpret these topics. PyLDOS is one of my favorite ways to do this. So for those who managed to get everything set up, you should be able to see something like this, which is pretty neat. So you can actually see, yeah, so you can actually see each topic and its break up words. So I'm just going to let you spend some time to explore this. Like on your, a lot of you have this set up, okay. So you can also see how much of the topics overlap. Like over here, these words, you talked about some words being in multiple topic models. For example, when I once did a really, really bad topic analysis on the Harry Potter dataset where I had all the books, and every single topic was just Harry, Hermione, Ron, like over and over again, 10 topics. So that was just all stacked on top of each other and it was absolutely terrible. So this is actually a really neat way to figure out if your topic model works or not. So after looking at this, I went back and added stop words and bigrams and so on and so forth. But yeah.
So the farther the bubbles are, the better the topic model is, right?
Well, that depends on.
I mean,
Yeah, it would mean there's less of an overlap. That's what I would like, yeah. But sometimes it makes sense for certain topics to be similar. It means that they have the same words.
so this LDA is internally uses spaCy for the dimension reduction.
Yeah? Okay. This is for topic 0. LDA model is. Well, that's odd, isn't it? I wonder. Yeah. Okay, well, we can move on to, we can talk about PyLDOS right after this. We're gonna start running up. So I just want to sort of round up what we've discussed so far. Yeah? I'm sorry? Are you looking at PyLDOS again? Oh, that's, yeah, so we're doing, like Lev was mentioning, since we're doing a PCA to break it up, it's axis 1 and 2. It should be, what? Yeah. So, well, my answer and Lev's answer is I'm not really sure because PyLDAWiz is not something I worked on before. But the way I use it is as a tool to find out if my topic model is rubbish or not. I don't actually use, for example, they talk about saliency and relevance over here in the bottom over here, and these are actually two terms I've not actually come across anywhere else and which I really don't know anything about. So I'm not sure the internal workings of PyLDAWiz. It's a third-party tool which I just use to visualize my topic model. So unfortunately, I cannot answer your question. Sorry. So you can actually use different topic models in PyLDAWiz. I've also, there's some tutorial notebooks which I've written which allow you to use like your own topic model and you can sort of break up. So basically you need to pass matrices which are document topic words and topic word matrices and which allow you to visualize it. What PyLDAWiz does is when you pass an LDA model, it does everything under the hood. So if you're interested in visualizing other kinds of topic models, then you can use the link at the end of this tutorial to do that. So we only have one part after this, which is topic coherence. So because we're at the end of our tutorial, I just want to talk about everything we discussed today. The main takeaway is really just spaCy and how to pre-process your text. Because like I said, topic modeling is something which you can really easily do. Topic modeling is just importing Gensim and running your topic model of choice, and then depending on your use case, figuring it out. What I wanted to use was topic modeling as a motivating example of why you need to properly pre-process your text, and why you should probably be using spaCy to do so. It's because you can after you finish using the spaCy pipeline to clean your text, you can also go on to use spaCy for using other things like someone talked about your language, your roots of your sentences and how you can visualize them. They have tools for visualizing your sentence roots. You can build neural networks and do sentiment analysis using spaCy. So there's a lot of alternate uses for spaCy apart from using it for Gensim for topic modeling. But in general, it's really important to know how to clean your data set depending on what you want to do after it. The topic models I got before I used spaCy were quite terrible. And it's really important to clean your data set before you go on to analyze it. So whether you're using topic models or Word2Vec or whatever you want to do, just make sure that you're being really careful. And each data set is going to look different. The one which we used over here was actually quite simple to clean up. For example, I worked with things like Facebook Messenger texts and WhatsApp texts, which can get really chaotic, in which case spaCy is really good for cleaning things up, and you can also use NLTK if you want to. But the real focus here is, spaCy, and I've added links all over the tutorial about other things which you can use using spaCy and Gensim as well. So please actually go back and make sure you have your language model set up and actually check these links out and use your own fun data sets and play around with it. You'll get really cool results. And before I finish up, we're going to talk about deciding which topic model is better. I had a question about someone mentioning how HTTP looked better than LSI. Now we can actually see if it is. So topic coherence was, I'm sorry. So you can see the next few couple of cells over here. We're going to run the last 4 cells, and what we're going to be doing is get a coherence value. Now, the whole idea of this is, again, some people talked about how you decide whether a topic is a good topic or not just by looking at a bunch of words, because each person interprets a topic differently. Topic coherence is a way for us to find out which topic is better from a human readability point of view. This was implemented last summer with the UMass and different kinds of, we have new kinds of topic coherence models set up right now, so you can actually get numbers now. You don't have to think anymore, and we can get a 0.56, which is greater than 0.50, and we know that topic model works better. So some important points to remember is this number is only for that particular data set. You cannot compare topic coherence values on topic models trained on different data sets. So you would need a topic model to be trained on the same data set before you actually use any coherence on it. If you can see what we've done over here is we created our topics for LSI, for HTTP, and LDA. We then created a coherence model, and we passed, we got our coherence values. And just so that we can plot this, someone said HTTP was better than LSI. Well, yeah, your hunch was right. According to the topic coherence measure which is being used, HTTP gives you the best value. Again, these are just numbers, and you should take it with a pinch of salt. Your topic, you might be absolutely convinced that your LDA topic model is better. That could be correct. Topic coherence is actually just one way to compare topic models from a quantitative point of view. You're actually going to find out a lot more about comparing topic models tomorrow. There's a talk on just about comparing topic models. So you're probably going to get more into the mathematical theory of topic models in general tomorrow. But for how to actually create a topic model, well, yeah. So I saw a hand up, yeah? Okay, so I don't actually know the complete, I just know the intuition. The intuition, I think, is human readability, which is what they talked about in the research paper. I'm not sure about the mathematical details. I don't know if Lev might know the exact. So the question was, what is the mathematical basis, or what is the intuition behind it? And as Lev explained, I'm going to be quite brief with it. It basically, they used a grid search to find out which was the better way to figure out which is the most human readable topic. So I've not read the research paper myself, so I'm just, yeah, you should read the paper if you're really interested in the mathematical basis. But the intuition is what's the most human readable topic. I don't use topic coherence too much. It's usually nice to just sort of have a rough idea, but normally you sort of look at the topics and use PyLDA-Wiz to get intuition. Again, I use PyLDA-Wiz just to visualize what my topics look like. I don't really read into the mathematical part behind it, which I probably should, but well, yeah, so now you know how to clean your extremely dirty data sets and how to get it ready for whatever text analysis you want to do. I'd like to thank Lev, who was my Google Summer of Code mentor last year, for being here and helping me out, especially with the math bits. I'm not so good at that. And if you have any questions, I'm here around tomorrow and day after as well. I love to talk about topic models and text analysis. I hope you're all going to use spaCy and install the language models. I'm sorry about that in the first half an hour. It wasn't as smooth as I would have wanted. But I hope everyone got something from this. And well, thank you for coming.